Good morning. I hope everybody's doing well. As you know, this is going to be the lecture on postmortem factors that affect meat quality. This is a follow-up of the lecture series that we had on pre-harvest factors, those things that we can do to manage the live animal. Now what we're going to concentrate on are the factors or technologies that can be applied at the point of slaughter and to the meat to impact meat quality. We're going to talk about electrical stimulation, blade tenderization, and aging. Those are very practical tools used in the meat industry. Then grinding, plant enzymes. We'll talk about enhancement, and then finally cooking. I also want to mention that on Thursday, we're going to be reviewing the 3 papers and having a discussion on pre- and post-harvest factors that influence meat quality. And also then a week from this Tuesday, we have exam B, which will cover up through pre- and post-harvest factors. And one thing I also need to let you know is that those that have scheduled an appointment on Thursday afternoon or Friday, I'm going to have to reschedule those due to a personal emergency. So thank you very much for your patience. So let's talk about how these factors are influencing live animals. So let's write these factors back up on the board, just like what we did for the post-harvest. So we know we have marbling, connective tissue, contractile state, and then degradation. And so what we're going to do is we're going to do just like what we did previously, but we're going to talk about electrical stimulation, blade tenderization, aging, grinding, and so forth, and how it affects those 4 pieces of the palatability puzzle. And I want to say thank you to Paige for recording this so that I could use the board. You know how much I love to use the board. So first let's talk about electrical stimulation. And we've talked about electrical stimulation a little bit, or alluded to it. And we have the paper, the Sable et al. Paper, and that talked about chilling, and electrical stimulation was mentioned in that. Electrical stimulation is a way that we apply an electrical pulse to animals in one of 2 places. Either in the blood pit, and we talked about it in the blood pit as far as helping with exsanguination, and then the other place is right, it's towards the end of the slaughter floor. We like to do it after the animal is eviscerated, either before or after hide removal and before carcass splitting, because you want to apply electrical stimulation to the full carcass before it becomes 2 halves. And what electrical stimulation does is, for a standard period of time, it the muscle the carcass is stimulated with an on-off, on-off, on-off pulse. What differs in electrical stimulation will be the amount or the amps used, the length of time, and the voltage used. So when we talk about electrical stimulation, usually we talk about low voltage electrical stimulation. That is done in the blood pit early on. Needs to be done during exsanguination as early as possible. High voltage or moderate voltage electrical stimulation is what's done towards the end of the slaughter process. And research has shown that you have about 60 minutes to apply the high voltage in order to get some effect. What electrical stimulation does is it stimulates the muscle to contract and uses up ATP. So it's really forcing rigor to go more rapidly. And that will also force pH decline. What we're going to do is we're not going to worry about how rapidly that muscle is chilled. We're not going to worry about the sarcoplasmic reticulum releasing too much calcium because it's too cold. It's pH is 6.2 and temperatures at 15 to 16 degrees C or less. We're not going to worry about that. Because if we use up all the ATP, We don't have to worry about the temperature. Let the calcium come. If there's no ATP, calcium can have no effect on the rigor of the contraction. It's also been indicated that on really high voltage electrical stimulation, you could get some muscle tearing. But I want you to know that in our industry today, the high voltage electrical stimulation is about 350 volts. The research that showed some muscle tearing here was 500 volts. OSHA will not allow us to use as high a voltage, even though it's segmented in a cabinet, and we worry about worker safety, because if you touch that carcass during the high voltage, it would kill a human, and we don't want that. So these are usually encased areas where the chain and the carcasses move through. The stimulation is applied usually through stimulation bars at the top, sometimes the middle, and sometimes the bottom of the carcass to get the electrical current to go through it. In the blood pit for low voltage electrical stimulation, that usually is some type of a clamp, or it's already grounded in some way, and it either touches the carcass or a clamp is put on an animal's ear, and that's usually at 80 or fewer volts. Most commonly about 60 volts would be probably the average. What electrical stimulation does, high or low voltage, it also reduces two-tone color. We talked about that two-tone color as a result of a pH gradient. So if you drive the pH of all the muscles much more rapidly, then you don't have the opportunity for that outside of the carcass that gets chilled more rapidly to stop anaerobic metabolism and have a higher pH. So we see more even color, and we see a brighter cherry red color that's more even, and because of that, we're able to see marbling. And if you look down here into these bead characteristics, I'm sorry, by putting this slide on this computer, the tabs didn't work, and this was supposed to be what characteristics in the carcass, what percent improvement do we see with a non-stimulated versus stimulated carcass. Lean maturity is a measurement of the darkness of the color of the meat. You look at the meat, and the closer it gets to real dark red, not due to dark cutting, but due to maturity, that's lean maturity. It should be a usable color or a bright cherry red color. And we see that lean maturity increases 23%, almost a quarter of 100%, just by electrical stimulation. And that's because it makes the color more even tone, it's easier to see. We also see about an 11% improvement in marbling score. Now I want you to know that marbling doesn't increase, but we're able to see marbling better if we have bright cherry red versus a darker red or two-toned lean. Lean color increases about 14%, and heat ring actually decreases about 23% in electrical stimulation. So we know that electrical stimulation also improves the muscle firmness. I don't know if you remember, but in the slide that I showed you with the two-toning, what we saw was, and I'm checking to see if, oh yeah, I did leave that in. We'll see that in a couple of slides. That in the two-tone meat, usually the center looks kind of soft. That's the lighter color, the lower pH. It may not be a PSE, but it's certainly softer due to the lower pH. It also helps to solidify marbling and make marbling more visible, and it definitely reduces the influence of cold shortening. So if we go over to our table here, let's look at marbling, and we're going to put electrical stimulation versus no electrical stimulation. Marbling improves slightly with electrical stimulation. It's only 11%, but so let's go ahead and put a plus. And I want you to know that the reason electrical stimulation was implemented in the meat industry in the late 70s is because of this. Because the only thing on this list, other than animal age for connective tissue, but in young animals, marbling is the only thing that has a dollar value. And I talked about spray chilling and carcass shrink in the last class period. If we can increase by 11% the high selects that are going to then grade choice, and you look at 350 head an hour times 16 hours times 5 days a week, and you have 11% of those that come over the line, let me tell you, that pays. That's a lot, or it's a great improvement in value, and it pays for itself. Connective tissue, there was work done to see if electrical stimulation, if the contractions, because contractions are a give and take. It's contract, relax, and it was originally thought in the late 70s that maybe paramecium or endomecium was getting torn, but it is not. So we're going to have no effect here, all right? Contractile state, this is the big one, because it reduces cold shortening. Now that doesn't give us dollar value because carcasses are not evaluated on whether they're cold shortened or not, but that improvement in color and the ability to see more marbling is a secondary effect, and we're lucky that it reduces shear force and improves tenderness. What about muscle fiber degradation? It does not affect the activity of calpain or calprostactin. But what it does do is if you eliminate cold shortening, it keeps from having that crowding effect. It's kind of indirect. I'm going to put a little tiny plus there, okay? Because if we don't have cold shortening, well, let me make it just a regular size plus. If we eliminate cold shortening, the degradation process can be maximized as far as what that muscle's capable of doing. In other words, we don't restrict degradation. So that's good. So electrical stimulation, we find that from a shear force value, and this is kind of a summary from lots of research, on your slide here at the bottom, beef, we see a 23% improvement in shear and a 26% improvement in sensory tenderness. So humans can identify it as different in tenderness. And when we do mechanical measurements of shear, we also see that improvement. But notice that electrical stimulation doesn't do anything for pork. And in fact, improper electrical stimulation or stimulation too soon will cause more pork to be PSE because it drives the pH decline so much more rapidly. And in lamb, we also see some improvement in shear and in sensory. So electrical stimulation, while it took a lot of money, certainly beef plants had to segment part of their chain to have this very protected area if they were going to do high voltage. Low voltage, they had to change a few things, not as big of a change in the blood pit, but both of those things cost money. That improvement in marbling and color really paid for electrical stimulation fairly rapidly within the industry. And we see here, this is from your textbook, you can see the stimulated pH decline versus non-stimulated, and you see that in beef cattle with stimulation, and this is maybe a little bit more rapid. I can just tell you 3-hour pHs usually aren't quite that low. I've taken lots of 3-hour pHs in my life. Usually we don't get to ultimate pH until about 9-12 hours with electrical stimulation. Where in a normal non-stimulated carcass, it'll be up to 18 hours. So it really does drive that pH, so we know that we're using up ATP. And if we look at stimulated versus non-stimulated meat, you can see that stimulation helps to keep the muscles from cold shortening so that we have shorter or longer sarcomeres. And we measure the effects of cold shortening by measurement of sarcomeres. We've talked about that in the past. And we know that in cold shortened meat, sarcomere lengths are about 1.8 microns. And in regular meat, about 2.0, 2.1 microns. So it isn't that big of a change, but it's big enough to make a difference. And if we look at this slide, this is the one that I showed you before with the pictures, but this is the two-toning I've been talking about. This is that heat ring. And you can see here, this is actually a stimulated and a non-stimulated side from one carcass, and it may be a little bit hard for you to see, but this has the two-toning where this one looks more solid, it looks a brighter cherry red, and they're from the same animal, they're just different sides. One side stimulated, one side not stimulated. We see that in as we talked about before, animals with less than 1/4 inch of fat that are lightweight or light muscled, those animals are going to be more susceptible to cold shortening, and electrical stimulation helps them. The nice thing is that animals that are heavier with more fat, that aren't going to chill as rapidly, electrical stimulation may not help them significantly, but it doesn't hurt them. So by stimulating all the carcasses that go through the production process, you make an improvement overall, because all those that would have been susceptible to the two-toning and those type of things, they get improved, but those that don't need it, they're just the same. And when we look at high versus low voltage, and this is just a summary of a number of research papers looking at pH at 1 hour, lean color, heat ring, so what percent of heat ring we have, and then shear force value. If we use low voltage and compare it to a control, remember low voltage is 80 volts or less, applied in a blood pit as soon at the point of exsanguination as possible. We notice that it does do some work. pH at 1 hour is already down to 5.8 with effective low voltage electrical stimulation. And lean color is becoming brighter cherry red. On this scale, a lower number is better. The heat ring is almost gone, 1.3, and shear force is decreased. Not a whole lot, but it's less. So low voltage does help. And there are plants that use a low voltage and then use high or medium voltage as well. If we look just at high voltage, and I'm going to just let you know that this high voltage is that 450 to 500 volts, not the 300 to 350 used today, so this is a little bit more severe. It's driving pH down. Just low voltage, because it's applied earlier, has a chance to get the pH down just a little bit lower. Lean color also decreased. It's the same as in low voltage. Heat ring is down as well, so high and low voltage don't really differ that much. But we see the shear force is a little bit lower with high voltage. And that's thought because the rigor of the contractions are greater. And these two slides up here, this is a relaxed carcass, and this is a stimulated carcass at the point of applying the electrical pulse. Most plants are going to do about 1.5 to 2 minutes, depending on the plant and the type of stimulation that they use. But what electrical stimulation does is it rotates between relaxed pulse, relaxed pulse, relaxed pulse. And it's, if high voltage, you get more rigorous contraction, and you're getting a little bit more muscle tearing in there. So electrical stimulation is a real important function within our industry. What's the second factor we're going to look at? Let's look at blade tenderization. So let me put blade tenderization up here. Blade. And this is blade tenderized and not blade tenderized. And blade tenderization is a very common practice. It's an old practice. It's where we use needles and we poke into the meat to disrupt the connective tissue and the muscle fibers. It does not change the shape of the meat unless you do it about 7 to 9 times. You know, one of those late nights putting a plan to operation, you gotta do something so you find out how many blade tenderization cycles before it starts turning into mush. What can I say? Most people are going to apply 1 or 2 passes of blade tenderization. It's usually applied at central distribution centers or fabrication specialists. I'm hoping on the field trip that we'll go to Standard Meat or to a location where they blade tenderize. One of the plants that I worked with when I was at Montford, we had a little bit larger, but pretty much this type of system. And after the meat is aged and it's ready to be cut or processed, then it's blade tenderized. And what you're going to now today, they usually have some interventions that are applied prior to blade tenderization. We'll see if my movie works. Oh, it doesn't. Paige, can you see if you can get the movie to work? Because what's happening here? Oh, good. See what it, screen, pointer, help, zoom in, I don't know. I know it's there in the system, so, oh, maybe hyperlink. You try the hyperlink and see what it does. Again, and hyperlink to, I don't know if it'll let you, yeah.
Let's try that.
Yeah, okay.
Oh, what is happening? Try this one?
No, it's I can't tell you what, go back and try this run program.
Oh, what did I just do?
Okay, and then run program, and then browse, and in the same folder, which is the post-harvest folder, pre-conversion.
Is it on your desktop?
It's on my desktop, yeah. Oh. Oh, what was that? Go back there. Collagen pre-harvest, right here, in this folder. Right there. Okay.
Yeah, it says something's there.
Okay, it's not gonna work, I'm sorry. We'll watch it work, I'll see if I can get it to work and bring it in. But there's a bay of needles, and it just pokes down in, and they usually are at anywhere from 3 to 5 or 6 deep in rows. And there's a conveyor belt, and this happens to be a top butt. It's laid fat side down, ran through there, and it goes up and down, and it puts holes in it. Because you're going through both connective tissue and muscle, you'll see some increased shrinkage after blade tenderization and vacuum package. But that's why you do it before you age, so that you're putting it in a new vacuum package, usually cut as a steak or pre-cooked or whatever you're going to do to it, because you are going to have some reduced shelf life. There has been a lot of concern with transmission of pathogens, because if you take and put a cocktail, a very high load, log 9 of pathogens on the surface of this meat and take the blades, they will take some of those pathogens inside. Pathogens will never be that high on this meat. And this blade tenderization's been done for over 50 years. And the meat that people eat cooked to the lowest degree of doneness will be steaks. Steaks are very commonly blade tenderized, and we have never had a foodborne outbreak associated with blade tenderized steaks. So it's a little bit of an overreaction, probably fine, because anything that cleans the meat up before it's processed is going to be helpful. These are the main manufacturers of these equipment. They're all over the place. All you have to do is go to Koch Industries or JBT or any of them, and they're going to have blade tenderizers that people use, and hopefully we'll get to see that. So we'll go over here and let's fill out our little chart. For blade tenderization, there's no effect for marbling. It's not going to really do anything to marbling. Connective tissue, blade tenderized, is going to help connective tissue. The contractile state, because it's going down into the muscle fiber, if you have cold shortened meat, it does help it. So let's put plus here, and degradation, there's no effect. So you can see as we start to build our piece of the puzzle, if we electrically stimulate and we blade tenderize, which most people do, we're having a little bit of effect on degradation. We're certainly helping contractile state. We're helping connective tissue here, and we've helped marbling over here. So we've helped all four pieces of our palatability or tenderness puzzle here, but not one. We don't use just one technology to affect all four in a positive way. So now let's go to the third postmortem strategy that's used to improve our palatability puzzle, and that's postmortem aging. We spend a lot of time talking about postmortem aging, and you should remember the sharks, the calpains, and the policemen, the calpastatins. And we know that if we have meat aging, that we're going to see an improvement. And we talked a lot and looked at the literature. So let me just put aging. And this means length of time stored in a refrigerated environment, not frozen. We know that as we age, we have no effect on marbling, right? We can't improve marbling by aging it. Connective tissue only with really high aging times. So I'm just going to say very high aging times, and we talked about 28 days or more will have a slight effect, only one plus. Contractile state. Does aging help contractile state? We know that if we have cold shortening, aging can't really proceed the way that it wants to, but once we have contractile state identified, aging doesn't really help that, okay? So it really isn't going to be a part of this piece of the puzzle, but obviously the big thing is right here, right? It's helping degradation. It's really helping that those structural proteins to be degraded and everything to fall apart, so we get ionic strength coming in and helping. We read a paper that there might be some other things going on that are signaling these. But we also know calpains and calpastatins need time to work. And this is a famous graph that was presented actually in the Gall paper and in the Taylor paper. And this is looking at time post-mortem from 0 to 336 hours. And this is shear force in kilograms. And what this is showing is that at 0, 6, 9, well, I think that's actually supposed to be 12, 24, notice that muscle gets tougher. That is during rigor, during onset. Now at 24, we should be at the end of onset and in completion. And then we see this big change within the first 72 hours, and then we continue to see some degradation as it goes down. And these are the actual kilograms that they reported. Yeah, 0, 3, 6, 9, 12, 24. They don't have all, I guess the dots are here. Okay, I said 0, 3, 6, 9, 12 are right there together. And then 24, and then 72, and 336. So we know that meat tenderization happens. We've talked a lot about it. We've seen that in the first 14 days. This is the slide I used before, that some animals got into this lower part or were tender after 7, but depending on calpastatin, we know that within 14 days, most animals are going to have the majority of their tenderization due to degradation, and it's going to happen. Okay, so we have 3 items up here. Let's talk about grinding. We know that meat that's tough because of connective tissue, really tough, like shanks, some of the other byproducts that aren't major subprimals, and meat from older animals, they're removed and used in what we call trimmings, and then they're used to make ground beef. So grinding is one of our age-old ways, and as a population in the United States, we love our ground beef. About 50% of the beef that we consume in the United States is from ground beef. So it's a major part of our beef consumption and our beef supply. So let's look at what happens. And I put on the slide, this is the oldest method. I think all of you know what grinding is. I put a picture of a grinder up on the slide, and we know usually it's a 2-part process where we do a coarse grind and then a final grind. And the final grinds usually are about 1/4 of an inch as far thickness in the as far as the plate, the little round holes in the plate. And what this is doing is reducing the effect of connective tissue, because the meat that we use in grinding is high in connective tissue. That's our strategy to get some value out of meat with high connective tissue. So for connective tissue, I'm going to put 4 pluses, because grinding really does influence that. Also, we see if we have, it doesn't really affect degradation. If we have contractile state problems, it will remove it. Remember, I told you the story about the cow carcasses that had the curved necks because of cold shortening. All that meat was ground, so nobody really cared. So I'm just going to put 2 pluses here. Marbling, there's no effect. And degradation, no effect. We're somewhat simulating what degradation could do in the fact that we're taking muscle and connective tissue and reducing it in particle size. But when we grind, we change the appearance. And it also has a reduced retail shelf life, or any shelf life, even if it's going into food service. And we know that we've had a lot of microbial issues with ground meat, because between coarse ground and final grind, we take meat, and usually this is done in 2,000 to 6,000 pound lots, depending on the facility. And we mix everything up, and we evenly distribute any microbial load in the product. So if we're going to have pathogens, they have a greater chance of getting them distributed into clean meat, and the product looks different. Ground meat definitely eats different than whole muscle meat. So, but great, we love it in the United States, right? And in other countries, they love ground meat too, but they tend to not eat as much as we do. Okay, so grinding. Next, plant enzymes. We've known about plant enzymes for many, many years. When I was as director of research in a major at Montfort, I played with plant enzymes for some of my customers. And plant enzymes are a great way to stimulate degradation. And some of them can also affect connective tissue. Really, it does nothing to contractile state or to marbling. Now, there are 3 major plant enzymes that are used. They are phycin, papain, and bromelain. And if you go to a seasoning supplier or a supplier and ask for plant enzymes, phycin and bromelain are usually sold together. Papain is sold separately. And phycin and bromelain are, if you look at this chart, you'll see that they have, this is supposed to be actomyosin, collagen is the second one, and then elastin. And physin is pretty powerful enzyme. It works both on the actomyosin, the collagen, and the elastin component. Bromelain works fairly well on collagen and a little bit on elastin. So basically, these enzymes just degrade everything. The problem with physin and bromelain is that at refrigerated temperatures, they are active. At frozen temperatures below minus 10 degrees Fahrenheit, they are not active, but between minus 10 and usually about 10 and 28, and remember meat freezes at 28 degrees Fahrenheit, they have some activity. So they're a little bit hard to control. And if your product's going to be frozen and you have a very controlled environment, you're going to do fine. I worked with a major company, because these are very powerful mixtures, and we were looking at producing fajitas from mussels that were not traditionally used, because skirt meat tends, especially inside skirts, tend to be higher in value with the pressure that the fajita concept put on them. So we found some mussels. They had tried it. They found that it worked very well. We took what they did, we scaled it up in the plant, everything worked well. Then we did our first trial in the store, and they got their meat, and the first day it was great. Because we had a very defined system of how long they could be thawed out, and then they had to be cooked that day within a certain period of time. The problem was that they didn't have orders for all of the meat, and they had meat left over, and they saved it for the next day. And you're not supposed to refreeze it from a food safety standpoint, which is very true. The next day they cooked it. It looked fine, but when they cooked it, it was mush, because the bromelain and the physin continued to work. And we basically figured out that if they cooked from the frozen state, they didn't have enough tenderization. If they cooked after the times that they had put for the control times, it was too mushy. And they really couldn't, from a production standpoint, stay within the window. Papain is a different story. Papain is temperature activated. So at refrigerated temperatures, it's not active, but it is active at 70 to 85 degrees C. And so there's actually a patent called Beef Swift Pro-10, where they did an antemortem injection of a solution of papain in water. They did this in the jugular vein of live animals about 30 minutes prior to slaughter. And this is the level of the patent, 0.5 milligrams per pound of live animal weight. So they weighed the animals. This is in the early 70s that this patent was put into place. The blood system would then distribute it, and when they harvested the animals, they would have papain. My boss at Monfort was a young meat salesman at Swift, and they had this new program, Swift Pro-10. He sold a truck load, 40,000 pounds of Pro-10 briskets to Barbecue House in Texas. The guy called him about a week later and said, I used some of those briskets. Oh, how did it work out? Well, we usually do about an 18-hour cook. Went in and I didn't have anything left, because the papain had gotten activated with the long, low cooking time. Jim said that's when he understood how papain really worked. I used a lot of papain, especially in corned beef briskets and in some of our high connective tissue cuts, because if I could cook it and control it. So we added that to all of our, we had corned beef brisket, we had some bottom rounds and some top rounds, and we had some pastrami and stuff like that. And I could use high connective tissue cuts that were cheaper, but then I controlled the cooking cycle. I controlled everything. I didn't give those raw to my customers and the restaurants to have them cook, because then I lost control and I didn't know how Papain would work. So, this is a system that can work, but it has to be highly controlled. Cooking. Cooking, I leave till last. Well, I have enhancement up here, but everything we've talked about in pre-harvest and post-harvest, and all of the things that we've done with the 4 pieces of the palatability puzzle can get eliminated by cooking. Cooking is a process of applying heat with moisture or without moisture. And we know that proteins, remember inside this muscle fiber, here's my muscle fiber. Remember that it's 17% protein and about 75% water. And the side chains of the protein are what hold the water. And we learned about bound, immobilized, and free water, right? Great stuff. We have a chance during cooking, we're going to inherently evaporate some moisture if we're not in an enclosed system. And cook on a grill, we should expect anywhere from 10 to 20%. It's really usually between 15 and 20% where we're going to have cook loss. And some of that's going to be heat evaporation, and some of that's going to be water coming off of the extra water coming off the protein, really out here in the free water, some of the immobilized water that then is available for evaporation. But how those proteins react, because during cooking, these proteins are going to go through heat denaturation. And we can either go through real extensive heat denaturation, or we can make it more gentle. And cooking methods really affect that. We also are going to have the effect of heat on lipids and heat on connective tissue. Connective tissue shrinks. Remember some of the Purslow work? It initially shrinks, but then they're at higher temperatures or lower temperatures, we actually don't have as much shrinkage, and the connective tissue isn't contributing as much to the toughness. Lipids are going to go through heat denaturation, and they're mainly going to affect flavor. So it is the muscle proteins and the connective tissue that really influence a lot of the tenderness and juiciness of these muscles. So, and we find that as we cook to higher degrees of doneness, and I just showed you some pork work and some beef work here, that this is degree C here, these are degree C. So this, this would be considered medium, so medium rare, rare, and well done. And we see shear forces just inherently go up. In this case, we have low select, high select, low choice, high choice. So you cook at higher degrees of doneness, it gets tougher because it's going to lose more moisture. We're going to have more protein denaturation. And those proteins, when they denature, instead of being like this, they go down like this. They shrink and they turn. And we have subunits twisting off. And we see that in beef and in pork. Keep hitting that. And this is just, but we also know we have some changes in flavor. So this is, would be medium rare and close to well, medium well done. And you notice that flavor intensity for select is less than flavor intensity for choice. And we are going to talk about flavor. We're going to talk about how during cooking and heat we end up with Maillard reaction products. Those are from non-enzymatic browning. What the cook yield of that product is going to affect, because that's a measurement of how much moisture we've lost. The degree of doneness, what cut it is, because cut is influenced by how much connective tissue is there and what cooking method we use, is all going to influence not only flavor, but also tenderness. And So there's a lot going on here. We usually talk about dry heat versus moist heat. With moist heat, we're gonna have minimum browning reactions with sugars, that's Maillard reaction, and we're gonna have less evaporative water loss. We use moist heat on high connective tissue cuts so that we can try to hold it and solubilize as much connective tissue. Whole muscle cuts like steaks, we like to do dry heat. And there you're gonna dehydrate the surface to get some Maillard reaction, browning reactions. And you're gonna have some evaporative loss, but if you crust that exterior, you're gonna get less evaporative loss. And we know that consumers like a little bit of grilling with their grill flavor with their meat. So how you cook it and whether you cover it or not will really affect it. Think about crock pot cooking versus cooking in an open pan with high heat. We know that the same meat is not going to taste the same. And we can look at different cuts. I put this up here because pan broiled, marinated, pan broiled, and braising. And this is to a lower degree of doneness. This is a very high degree of doneness. And when you go to those high degree of doneness, a lower number means that it was not as juicy. It was also tougher. It had less connective tissue, but it also had less flavor intensity. And the shear force values, though, were interestingly about the same because of the connective tissue contribution. So we have each cut has its own cooking optimal method. And we just finished a big study called the Flavor Myology Project. It's a 2-year study that we did when we were with Colorado State University, and I'm going to show you some of the things. So cooking is a really, really important part of this. And so we're going to talk about this because I'm going to, when we discuss the papers, the 3 papers, make sure you've read them and thought about them. I'm going to bring in the Australian MSA system, and it has different cuts and different cooking methods